All right, so in lesson 6.2, it's like I didn't save it, but we just sketched the graph, right? Or were we about to sketch the graph?
No, you're halfway through B.
Okay. Oh, that's right, we sketched the graph at 6.1. All right. So we were just finishing the stoichiometry step, and I think we were ready for the equilibrium step. So the initial volume, we had moles, and this is the number of moles at the equivalence point because it's the number of moles of this propanoic acid that we started with. If all of the hydrogens reacted out, this is the number of moles at the end. So the concentration of this particular ion we have is 0.060. So the problem we have now is this is a weak base solution. Because we have a conjugate base, it's going to start pulling hydrogens from waters to create propanoic acid again and leaving us with a bunch of hydroxides floating around. So this is the reaction you're going to see. With this conjugate base reacting with water, and you end up with, here's your propanoic acid, 5. And then hydroxides. And this hydroxide is why the propanoic acid is acting as a weak base. Because propanoic acid is very weak. And so you don't want a solution just full of propanoate. It's going to start pulling the hydrogens. That's where you get these. And so we want to fill in some of the concentrations that we know. After the stoichiometry step, we have 0.060, and that's molar. We can just leave it as concentration for now. Water, we want to just ignore it. At the start, propanoic acid and hydroxide are both 0 because at the end of the stoichiometry step, they've both completely reacted out. This is the shift to equilibrium. All of the coefficients are 1. So this one's going to go down by x. These will both go up by x. And our equilibrium concentrations, 0.06 minus x, here's x and here's x. So we're going to use the equilibrium expression here. Kb equals concentration of the propanoic acid. It is not working. This is your equilibrium expression for this reaction where propanoate is acting as a weak base. We have x's for all of these, so it would be x, x, and then just 0.06. But we don't have Kb. What we do know is a relationship Ka times Kb is Kw. And we do have the Ka. Ka for this acid, you have to look up at the very top of the page, 1.3 times 10 to the negative fifth. get 7.7 times 10 to the negative 10th. And we're going to start plugging in our numbers down here. So propanoic acid is X, hydroxide is X, propanoate 0.06 minus X. We're going to get rid of this to make our math a little simpler. And then X equals 6.8 times 10 to the minus 6th molar. What we really want to know here is the pH. This is the hydroxide concentration. And like I've said before, there's two ways that you can do it. You can use basically the relationship where Kw is the concentration of hydrogen times the concentration of hydroxide. That'll give you the same answer as if you used POH and then subtracted that from 14. I tend to think that one is a little bit easier. The POH is something in the 6 range. It's actually 5.17. And you get a pH of 8.83. Okay, so it says sketch the titration graph. Describe the major species at the starting point, at the halfway point, the equivalence point, and past equivalence point. So let's draw a graph here. pH is on the y-axis. It goes from 0 to 14. This is milliliters of sodium hydroxide added. This is exactly the kind of graph that you're going to have with this lab that's coming up. At the starting point, what do we have? So you might need to look back through all of these. What do we have originally for our starting point? What's in this solution? Colin, what's in the solution?
Okay, that's right.
So when we started this thing, before we started adding sodium hydroxide, all we had was this propanoic acid, which we'll call HA. A is just the anion, and it's easier than writing propanoate. So all we have is this weak acid. Do we know its pH at the very beginning? We didn't actually calculate it. It's somewhere around 2. So it's not extremely, it's not like a strong acid where it'd be 1, 0.5, or 0, but it's still fairly acidic. How many milliliters of sodium hydroxide did we need to get to the equivalence point?
45.
Yeah, for the equivalence point, it's 90. For the halfway point, 45. So, do we know the pH at the halfway point? What is it?
4.89.
So 4.89, so something about here. And the graph will probably look something like this. They usually are fairly steep in the beginning, and then they level off with a mostly shallow slope. What's the pH at the equivalence point when 90 milliliters have been added?
8.83.
So about here. So they usually continue like this until they get close, and then it goes up steeply like that. And then it'll level off somehow or another. So at our starting point, we had pH of maybe something around 2. All we had was the weak acid. Then we get to the halfway point. What species are present at the halfway point? We have some of our weak acid still, and some of it is the anion. At the halfway point, the relationship is actually like this. They're the same number, right? So if you divide one by the other, it's equal to 1. Somewhere in the middle of this extremely steep slope, and you have to eyeball this. So you'll graph it, and then you'll just kind of pick the best spot. So you want it to be where this leg is probably about equal to this leg. So you'll find your equivalence point. What do we have in the solution at this point? Do we have any weak acid here? There's no weak acid. There's no hydroxide either. The only thing we have at this point is our conjugate base, the anion. In this example, it was the propanoate. It's also asking about the past equivalence point, and really what it's talking about is just anything after here would be considered your past equivalence point. So what do you have in the solution after you've gone past the equivalence point? Do you have any weak acid? No. So no weak acid. How about the conjugate base? Do we have any conjugate base? We do. We're going to have all of this amount of conjugate base. You're going to have a lot of sodium hydroxide because what this is telling me is that I've continued to add sodium hydroxide even after we've gone past it. So concentration of sodium hydroxide, which you could say is the same as the concentration of hydroxide. pH here was what, 8.89? 8.83. So this represents part 3 of the lab. Part 1, you're just trying to figure out the concentration of sodium hydroxide using a specific procedure. Part 2, you're trying to figure out something specific. And part 3, we're trying to figure out, I believe, the Ka of the acid. And so you're going to have to use a pH probe, and you're going to get, I don't know, it's probably going to end up being 100 data points, give or take. You'll make your graph, and then you'll use this information. Now, it's probably not going to ask you to label everything, but you will, use these numbers. Suppose 100 milliliters of a 0.15 molar propanoic acid solution were titrated with sodium hydroxide solution instead. How would the pH at the halfway point change? Would the solution at the halfway point be more or less effective buffer? Pause, we forgot to put in one thing in this particular graph. Where's the best buffer? The halfway point. So the absolute best buffer would be here because we have equal amounts of the weak acid and the conjugate base. But this is not the only place where you could have the buffer. Anywhere from maybe here to here would be good. And we call this the buffer zone. So in the buffer zone from the halfway point to right here, what do you have more of, the acid or the anion? The anion. So the anion to this is greater than 1. In case you want to know why I keep writing it as anion divided by weak acid, it goes back to that equation, the Henderson-Hasselbalch equation. Plus the log of anion divided by weak acid. From here to about here, we have more of the weak acid than the conjugate base, so it's less than 1. But the best buffer is exactly at this point right here. And that's where the ratio of anion to weak acid is exactly equal to 1. And the log of 1 is 0. So the best buffer is where the pH equals the pKa. This is always a multiple choice question. Just as a note, the more multiple choice questions you get right, the less stress it puts on the free response. The free response gets the majority of the time in the class. But if you get 20 right out of 50 on the multiple choice, then you've got to dig your way out of a hole. Whereas if you get 35 right on the multiple choice, you've got a lot of wiggle room. And the chance that you can dig your way out of that's pretty good. If you do well on both, there's a good chance you get a 4 or a 5. So this question B3, Suppose we add 100 milliliters of a 0.15 molar propanoic acid solution titrated with sodium hydroxide. The difference here is we started with more of the acid. If you look at the original experiment, we had 60 milliliters of our propanoic acid. Here we have 100. How would the pH at the halfway point change? What's the pH at the halfway point going to be if we start with more acid? I get a lower, I get a higher. It's not going to change. It's going to be 4.89 because of this relationship right here. pH equals the pKa. The Ka is a constant. Trick question. Doesn't matter if we start with more acid. At the halfway point, that number is going to be set. Said, would the solution at the halfway point be a more or less effective buffer? It would be more effective because there'd be more of the acid to react. That's basically it. The higher the concentration of the acid, the more you can move left or right and the buffer still works. I guess up to this point, we haven't really talked about what's the point of a buffer solution outside of textbook reading that you did about a month ago. There are times when we want to make a buffer solution, and that's where we have the weak acid and its conjugate base. The whole point is that it can resist changes in pH. If you add a base to it, you'll see a shift in the pH, but it'll be small. It won't move very far. The whole point is to keep the pH constant. So here, if you added a little bit of base, it's going to move a little bit, but its pH didn't really go up that much. If you added some acid, it would change a little bit, but it didn't drop that much either. It's just a way of keeping the pH constant. If you didn't have a buffer solution and you added sodium hydroxide, you'd be looking at something like this, where the pH goes from maybe 6 to 12 very quickly. Because at this point, there's nothing to absorb that change in the pH. And you can find buffers all over the place. When we calibrate our pH meter, it's done with a buffer because I don't want it to change. But like this nasal spray, if you look at the ingredients, it says it's an isotonic solution of sodium chloride, 0.65% in deionized water. And the second ingredient, monobasic potassium phosphate / sodium hydroxide buffer. What's the point of the buffer? It's to stabilize the pH. They don't want something to happen to this and have a huge drop in pH, and then if you shoot it in your nose and you have an acid, it burns. Or if the pH got really high, if you put it in your nose, again, it's going to burn really bad. And so the pH is stabilized somewhere around the same as your tissue. It's usually about 7.4 is the pH in your body. That's what it's supposed to be. And so it's a buffer so it doesn't go one way or the other too far. This one's got disodium phosphate and monosodium phosphate, and it doesn't really specify that it's a buffer, but you have two with the same anion. And so that might give you the hint that it is some sort of a buffer. Your blood has a buffer system. Blood pH is pretty specific. It's got to be between 7.35 and 7.45, excuse me. If it's outside of those limits, like you really don't have a lot of time. You got to be in the hospital and get treated quickly. Seriously. But your body is really good at absorbing those changes in pH because your blood is a buffer. And it's not just two things, it's actually made of three things. This is an aside. The blood buffer. So you want the pH 7.35 to 7.45. There are three things in your blood. The first off is, what's the name of this ion? Bicarbonate. So here's bicarbonate. What's this one? And what's this? Carbon dioxide. So these three things are working together. Carbon dioxide is not just a waste product that your body has to get rid of. It's true, it is. If there's too much, it needs to get rid of it. But carbon dioxide plays a pretty important role in stabilizing the pH of your blood. If it starts to shift too much one way, so let's change this one to H2CO3, carbonic acid, bicarbonate, carbon dioxide. So usually it's here, but if your blood starts to get too basic, it shifts this way, lets off a hydrogen, becomes more acidic. If you get to the point where your blood is too acidic, so again, we're starting here, too acidic, what happens is it shifts this way and it absorbs the H plus and keeps you in this nice little range right here. Your body is very good at it. I'm gonna make everybody do push-ups after this.